Good afternoon, everybody. Welcome to the Dynaflow Lectures. My name is Frank Bos, and on behalf of Dynaflow Research Group, I will be your host this afternoon. Today, Richard Fawcett will give a talk about the potential impact of dynamic events on your piping system. As a senior engineer, Richard has significant experience in solving this kind of problems. He will also address various ways to deal with these problems using pipe stress software like Caesar2. After this presentation, feel free to join us and have some drinks to close this session. Richard, the floor is yours.
Okay, hello. As Frank said, today we're going to talk about dynamic phenomena and how would you actually incorporate that in a stress analysis. We're not just going to talk on pipe, and we'll also cover a short example with pressure vessels as well. So, first of all, typically it's becoming more common to actually have to include dynamic phenomena in a pressure vessel or piping calculation. For example, how do you include acoustically induced vibrations, or the change in the temperature of the fluid within the piping, or pulsations, or vortex shedding. And what we're trying to do today is we're going to try and look at a range of different transient events. What are they? When might they actually occur? And also what their effect on stress analysis is. And with the help of a few examples, what we're going to try and do is show you how you'd actually incorporate these effects and actually calculate whether they're important for your system or whether you have to change it. Okay, so first of all what we're going to do is we're going to introduce a few transient and dynamic phenomena. Then we're going to look at some general characteristics about these phenomena, and then we're going to ask the question, what sort of options are available for you to analyse them? And then, with the help of a few cases, we're going to show you the use of some of these analysis methods. And then we'll just close with a few closing statements. Okay, so these are not all the transient and dynamic phenomena that could occur, but we're going to just give an introduction to a few. So for here, we're going to touch on acoustically induced vibration, often called AIV, vortex shedding, flow-induced turbulence, pulsations, surge and Waterhammer, also slugging, and thermal transients. So first let's look at acoustically induced vibration. And this tends to occur downstream of large pressure reducing components. For example, if you've got a choke valve in a wellhead, which we'll touch on later. Also orifice plates with a very small orifice diameter. And what will tend to happen is you'll develop downstream is a lot of kinetic energy in the range of 500 to 2000 hertz. And this acoustically induced vibration tends to excite breathing nodes. It doesn't tend to, it can excite breathing nodes, which is shown on the lower left corner in the wall of the breathing node in the wall of the pipe. What you'll see here what's called lobes. You'll see you've got a sort of sinusoidal profile along the length of the pipe and also around the circumference. Okay? And exciting these can often lead to problems and fatigue failure. And I've highlighted here about small bore connections which are in the wall of the pipe. And in the connection region, if such breathing modes are excited, this can lead to particular problems at these small bore connections. Okay. Second problem we look at is vortex shedding, or sometimes called flow-induced vibration. And there's two mechanisms where this can occur within the piping system. And on the left-hand side, what we're showing here, is what's called a side or a dead leg branch. For example, what you'll see here, this is 3 outlet lines from 3 compressors. Okay? And if we just take, it's just an example, but if we show you that one of them is in action, one of them is working, the other 2 are switched off. So that means we're closing the valve here, and this one isn't working. Flow will pass out, and we'll move along the header. Because the closed branches will act, or can act, as Helmholtz resonators, then what can happen is vortex shedding, shown on the lower left corner, can occur downstream of these branches and pass into the piping system. On the right-hand side, so there's a second mechanism where we can actually have vortices in flow. And this is if we have a probe hanging into the pipe. Okay? And what this photos, flow-induced. It's a photograph of flow field downstream of a cylinder with vortex shedding. You see the vortices moving downstream away from the cylinder. And this can also happen downstream of a probe, depending on the flow conditions and the Reynolds number. Okay, now we're going to look at here, flow-induced turbulence. So there's a slightly different frequency range to acoustically induced vibration. And this tends to occur downstream of discontinuities in the flow. So also partially closed valves, but also, as the example shows here, a bend. And what we see in the CFD image on the left is you'll see an incoming gas stream, which is uniform, denoted by a uniform velocity, about 8 meters a second. And as it passes through the bend, what you'll see is a separation, a low velocity region, which is on the inside of the bend. Okay? And because of the shear layer between the stagnant region and the high velocity flow, you end up with the generation of a large amount of turbulence. This is a broadband turbulence, and will lead to kinetic energy regions in the flow. And this problem is particularly important for high velocity systems, okay? And because the turbulent kinetic energy that is developed will be proportional to the velocity squared. Okay. Okay. Now we look at pulsations, and most frequently encountered system where these would occur would be reciprocating compressors and pumps. Okay. And what we're showing on the lower left, if the gas comes in, it will be compressed, you'll come in, you'll close the valve, then you'll compress it with the piston at a certain time, which you're at the pressure, you'll open the outlet valve, and the flow will pass out of the compressor cylinder. And this will lead to a pressure profile, which we've drawn here schematically, which has a spike profile. These pressure pulsations will be typically damped on the exit of a compressor using a pulsation bottle. But even so, it's possible you end up with pressure pulsations of around 2 to 3% on the exit of the compressor after the pulsation bottle. And these pressure fluctuations can lead to excitation of mechanical resonance modes within the piping, thereby giving the cyclic nature of the pressure fluctuations, fatigue failure. Okay. We can also look at sort of one-off pressure surge or a Waterhammer event. And what we're showing here on the right-hand side is a valve which has failed due to excessive pressure. Okay? And this pressure has occurred due to the fast closure of a valve. So, for example, an emergency shutdown valve is closed in a number of seconds. Okay? And this leads to a pressure peak upstream, and can also lead to a cavitation, implosion cavities downstream. Okay? And these pressure fluctuations will once again lead to unbalanced forces in the piping, and also high levels of dynamic stresses. Okay? What we're going to show on the lower right, showing you a video, this is a video I'm going to show on the next page. And this video is taken from experiments that were done by the University of Karlsruhe. Okay? And what we're going to show is, on the right-hand side, this valve, which is closed a very short period of time, about half a second, I believe. Okay? And what will happen? The flow is moving from right to left. And at the beginning, it is totally full with liquid. Okay? And what you will see is around this region here, you'll end up with, because the flow is moving away, you'll end up with a void, and you end up with a low pressure region, where the flow, the liquid will reach the vapor pressure, and a cavity gas will be formed. And you will see that will then implode, and I don't think we've got sound in here, so we'll have to just see what happens. Right. What you'll see now is it's actually on. So what we saw there, there you go. So what you see the example of the sort of force and the dynamic pressures that actually occur. So you see the flow move away, you see the void forming, then the pressure recovers because the lower pressure in the void, and the flow moves back towards the valve, and then ricochet, move away again. That is an example of pressure surge downstream of the closing valve. Okay, you can also have, that was an example of a multi-phase flow, but you can also have multi-phase flows that occur on a more cyclic nature. Okay, and on the left we're showing a number of different multi-phase flows. For example, on the top one you've got a number of gas bubbles within liquid flow, and we move through at the bottom to an annular flow where you have gas in the middle and liquid around the outside. No, sorry, gas in the outside. Yeah, that's right, liquid on the outside. But the most important piece for transient effects is what's frequently come across, which would be slugging. It's the middle one, this one here. And what you will see is you see a mixture, you see the part of it is gas here, and you have liquid here. Okay? And because of the difference in density between a liquid and a gas, then you'll have a change in the momentum and the reaction force acting on the bends. Okay? And what type of multi-phase flow regime. This is a typical graph on the right-hand side, which, based on the normalized liquid velocity and normalized gas velocity, will give you an idea of which flow regime you can expect in your multi-phase system. By normalized liquid, what I refer to is basically you have the liquid fraction, you divide that by the cross-section area. Okay, so the final one we want to introduce is having a cyclic temperature profile. Okay? So for example, a lot of process vessels, for example a dryer, will lead to a cyclic temperature profile. For example, just scroll schematically, you start here at 30 degrees, during the process it will go up to 300, then it will decrease, and then repeat. Okay? And here what's shown in the lower right corner is an example of an air-cooled heat exchanger. Okay? And what the typical problem is, for example, the heat transfer rate between the fluid and the metal will depend on what is the heat transfer coefficient, okay? And that is largely dictated by the flow speed. So for example, in this example here, in the nozzle you get a much higher flow speed than you would in the header box. So you can end up with a situation where the nozzle heats up or cools down much quicker in the header box, which will lead to thermal stresses in the intersection. Given the cyclic nature, this can also lead to fatigue problem. Okay, so what I've done there is I've just introduced a few different types. Now what I want to do is just describe a few of their general characteristics. Okay, so we're talking about different types of transient events. So, I've shown a number, but we can also make a distinction between which ones are broadband and which ones are tonal. In a broadband, something like acoustically induced vibration, where it occurs over a wide range of frequencies, but of a relatively lower amplitude, because your energy, your dynamic fluctuations, are divided over a wide range of frequencies. On the right, with a tonal excitation, then kinetic energy or dynamic effect is concentrated at one frequency. Okay? And this would be something such as compressor pulsations, or a surge event. Okay, now what about the distinction between a forced or a resonant or resonance? Forced response or resonance response. So what's shown here is all systems have mechanical resonance modes. Okay, for example here is just typical mode shape, and this has a frequency of 4 Hz. Okay. Now what I want to show here is the distinction between when does a flow-induced vibration lead to a forced response or a resonance response. So what's shown here is this is a frequency spectrum of flow-induced vibrations. Okay? So you see here amplitude, peak here, peak here. Okay? And what's shown here in this middle line is what are the mechanical response modes of our system. Okay? And what you'll see, this is on our mechanical vibrations, so what we actually measure in the piping system. And what we're seeing is here we have an overlap between the flow-induced vibration, the mechanical resonance mode, which leads to a larger mechanical vibration Now in this case, on the left, well, we have flow-induced vibration that does not overlap with mechanical resonance modes. And this referred to as a forced vibration. And the flow-induced vibration is not exciting a mechanical resonance mode. Okay. So to give an example of sort of effect this can have, this is a header, which then passes through vertical line and then moves into another header here. This resonance mode has a frequency also of 4 Hz, coincidentally. Okay, and your excitation is an unbalanced force due to a slug load of around 10 kilonewtons. And what we're going to just plot is what is the difference in displacement at the elbow? What is the amplitude of the excitation? Okay, and this was a slug that was caused during startup of a steam system. Okay, and we looked at different slug lengths just to get a variation. So 5 through 50 meters. And these gave you a passing frequency of the slug. So it went through 10 through to 1 Hz. Okay? And what you see when you calculate what is the elbow displacement, that you get the largest displacement around a 5 Hz passing frequency. For the same applied unbalanced force. So we have 10 kilonewtons for all 3 slug lengths. And we end up with the largest displacement for the 5 Hz passing frequency, because we excited the resonance mode, 4 Hz, whereas these are more of a forced response. Sorry, the lowest 2. This one, 10 Hz, this one, 1 Hz, more of a forced response. Okay, and the final distinction we want to make is between a cyclic event and a one-off event. So a one-off event, shown on the left, occurs or during a surge event, or external blast load, or also something like slug load times the starter. Okay, and here fatigue isn't really a problem, and you want to be calculating more against what is the ultimate yield strength of your material. You'll calculate that as an occasional load. Whereas a cyclic event, such as due to a pulsation, then we're looking at more large number of cycles, and fatigue becomes our concern. And our allowable limit becomes the endurance limit of the material. Okay, so just to group those different types of characteristics, saying tonal or broadband. So is our dynamic event spread over a wide range of frequencies? Is it broadband? Or is all the kinetic energy concentrated one frequency or a number of frequencies? Okay. Force response, is our flow-induced vibration, is it exciting a mechanical resonance mode? If so, a smaller flow-induced vibration can lead to a larger mechanical response. Or is it a one-off or cyclic? So do we need to consider it as a fatigue issue, or is it a one-off that we can consider calculated against a yield limit? Okay, so we've explained different phenomena and also an overview of grouping them into different categories. Now the question is, how can we analyse them? Now what I've tried to do is go through everything. I've tried to give an overview of the different types of limits that you can have. The first is the geometry or process-based limit, which we can often use as a screening stage. We can then go on to vibration-based limits, and then we can go on to a stress-based limit. Okay. So there are codes available to assess flow-induced vibrations in piping systems. The most commonly used nowadays is the Energy Institute document, Avoidance of Vibration-Induced Fatigue Failure. And what I've shown here is the Vortex Shedding assessment procedure from this code. And what you'll see here is you're calculating here parameter D, okay? And this is calculated based on a number of parameters, including the density and the flow velocity. And you work through this flow chart, and what you'll end up with is at various points you'll end up with what's called a likelihood of failure. Okay, see here we've got 1 and here at 0.29. And based on this likelihood of failure, you can determine, is my system suitable for avoiding vibration-induced fatigue failure, or do I need to make modifications? So if you don't conform with the required likelihood of failure, then you need to make modifications to your system, or we can consider a more detailed analysis. Okay, these limits, these process-based limits, are based on experimental results or field observations. So for example, shown here is a limit for acoustically induced fatigue, okay, AIV. And this is taken from the paper by Eisinger in 1997. Okay? And what I'm showing on the left is a plot here. This is the acoustical power. So this is the acoustical power that is calculated downstream of the valve. We'll show in more detail later how that is done. And then below, I'm showing you geometry parameter of a system. So that's the diameter of the pipe divided by the thickness. Okay? And what you showed is based on this line. You could make this is based on experimental observations and field data. Show that all the systems below this line, the dotted line, in white, did not fail. Okay? So here there's no failure. And then above this line, it was seen there was a number of failures. Okay? And based on this data, which applied in an earlier paper, they determined this limit. Okay? And this limit is, for example, included in the Nozzle code. Okay? And then move on to the next level. So if you don't conform to such a geometry or process-based limit, we can go to a vibration amplitude-based limit. What we show here, for example, this is a frequency spectrum. Okay? Frequency spectrum would measure the vibration from the field. You can also get this from a Sator calculation. And you end up with, sorry, it's vibration. You see here we've got a frequency of around, I think, 6 or 7 hertz, an amplitude of 30 millimeters per second. And what we can do is we can plot this on a VDI graph. So this is the German code for German guidance code for assessing flow-induced vibrations. Okay. There's also a similar graph in the Energy Institute document, and there's also one in API 618 for assessing pulsations. Okay. And what we'll do is plot this on the graph, and we see that we're lying in what's called the danger region, meaning our system does not follow the guidelines from the VDI document. Okay. So the next question is, if we don't conform with this limit, what's the next stage? So we're going to move on to look at stress-based limit. Okay. And with the stress-based limit, we can do a calculation in a piping stress package, such as Sazer, for example. Okay. And just to give you an example of how you could incorporate that, if we're looking at a pressure surge, so we've got a pressure peak going through a system, then we'd end up at a certain moment, pressure here, pressure 1 at one elbow is lower than the pressure acting at the second elbow. Okay? And this pressure difference between the two we can use to generate a force, or an unbalanced force, acting on the piping. Okay? That unbalanced force we can bring into our piping calculation to actually calculate what are the stresses arising in the system. Okay? Then once we've calculated those stresses, we can then use that dynamic stress to calculate what is the allowable number of cycles for a given scenario. Okay? And we can do that with design curve. So this is a design curve from the 13445. It's also equivalent in Section 8, Division 2, to determine how many cycles we can have of a given stress level. Okay. Just to give you a sort of overview of the three type of methods we've been talking about, we can start with the geometry or process-based limit. This is typically very easy to apply on a whole system perspective. You have to deal with the spreadsheet. However, there is a level of conservatism in this, and moving through to look at for the ones that fail that with a more based on amplitude, based on displacement amplitudes, and also stress-based limits. You would increase the calculation time and complexity, but you'd also increase the accuracy of your calculation. Okay. So I gave you an overview of the phenomena. We've talked about their general characteristics, the methods we have to analyse them. But now we'll go through a number of cases where we'll address those methods in much more detail, So I've chose a number of cases based on projects that we've actually done at Dynaflow. issue 1 was look at flow-induced vibration assessment of a wellhead line that flows on a oil and gas platform. We're going to look at a thermal transient assessment of a nozzle intersection in a vessel. And then we're going to look at vibrations in an existing process line. Okay? And from these we'll actually explore different analysis methods that we've just introduced in the previous section. Okay. So just give you an overview of the wellhead line. What I've got here is the wellhead comes from the Christmas tree. Okay, moves up, goes to the choke valve, and at peak flow conditions, we have a pressure drop of around 100 bar across the choke valve. Okay, flow then comes down. We have a number of short dead end branches, which have block and bleed valves on them. Little block and bleed valves move along. It's supported with a hanger to allow movement of the wellhead. Then we'll move down. We have this gas tapping line. Take gas samples from the line. Okay? Then move down, and then joins into a manifold around this section. Okay? Now, the question is, what dynamic effects do we want to, what possible dynamic effects can occur in this line that we need to analyse? Okay? So we're going to look at first the choke valve. This is a schematic picture of a choke valve. You see you've got pressure coming in. I realised I've done this the wrong way around for my example. But we're going from an inlet of 180 to 80 bar. So we've got a pressure drop of 100 bar. Okay? And if we remember from the examples we introduced at the beginning, we've got the first problem, we've got a large pressure drop. Okay? So we've got a possibility of acoustically produced fatigue failure. Okay? And we're going to look at that with help of the process-based limit. We've also got the pressure with such a discontinuity chance. We will create flow-induced turbulence. We need to assess that. I'm going to do that with the help of the stress-based limit. Okay. On the right, we've also introduced the dead-end branches. Now, if you remember at the beginning, we talked about these could induce vortex shedding within the pipe. Okay. And we're going to analyse that from both a simple process-based limit and then also, for the more critical case, a stress-based limit. So just give an overview. We're going to look at choke valve for acoustically induced fatigue, flow-induced vibration, and flow-induced turbulence. And then for the dead-end branches, we're going to look at flow-induced vibration, vortex shedding. Okay, so remember we talked about the icicle limit a few slides ago, when we looked at the acoustical power level and compared that with the limit based on the geometry of your piping. So what we're showing here, this is the flow over a valve. So this is our choke valve. Okay, we've got a pressure difference delta P. We've got the upstream and downstream. No, upstream, static pressure and temperature. Okay, we've got a volumetric flow rate, upstream volumetric flow rate. Okay, and this limit calculates what is the acoustic power generated across the valve. Okay, in decibels. Okay. If we compare that limit, it gives us this straight line, such as this. Okay. No, sorry. This straight line limit is the, remember from the previous data, showing this was where the failures occurred, and this is where there was no failures. Okay. And what we're doing is we compare our sound power level of 160 dB with that limit. Okay. Now, what is important here is what is the D over T ratio of our pipe. Okay. Now it says 6 inch, so about 150, 160 millimeters. With schedule 80, which is 10, 11 millimeters. And we come up with a D over T of 15. So we see here, we're well within the margin from icicle. Okay. However, what's interesting is if we were to have the same power level, okay, but a much thinner pipe wall, then we'd move into the region where we might expect failures. Okay. Okay. So flow-induced turbulence. Okay. Now, what we're saying here, we said the turbulence that's generated is broadband. So that means you've got the energy, the kinetic energy that's generated, is distributed over a large range of frequencies. Okay. And what we've got is our problem is mechanical resonance of our system. Okay. There's two methods that we can cause mechanical resonance. Okay. Option 1 is the broadband turbulence directly excites the mechanical resonance. So for example, if it's over 1 to 20 hertz, has energy at all of those, the mechanical resonance is at 10 hertz, then the energy at 10 hertz in a broadband turbulence will excite that mechanical resonance mode. An alternative, which is often called a perfect storm scenario, will be the broadband turbulence excites the acoustical resonance mode in piping. Okay, and I'll show you the next slide, which then in turn excites the mechanical resonance mode. Okay. So to give you an example of exciting an acoustical mode, this is taken from a book by Blevins, and what he showed with various data is this is the broadband spectrum downstream of the valve, okay? And what you'll see is you end up with these peaks in the turbulence spectrum, okay? It's the first mode, second mode, third mode, okay? And this was the turbulence exciting acoustic resonant modes within the flow, okay? So these aren't mechanical, and these acoustic modes could then excite mechanical response modes. Sorry, just to show you there's all different graphs, just depending on what is the power condition of the compressor in the system. So just concentrate on the one here. You see as you load, it's just the compressor loading in the system. Okay, and Blevins, from comparing different sources, said that if you were to excite an acoustical resonance mode in the system, that you get an amplitude of 1 to 2% of your pressure drop across your valve. Okay, so what are the acoustic response modes of our line? Now, to determine this, we actually put this into our Boss fluid, which is a acoustical, method characteristic solver for flow transients, and we introduced a step inputs at the inlet of the system. Okay, and from that we excited the acoustical resonance mode of the system. Okay, and of course there is some unknown given you're connecting to a manifold here, but for all the situations that we analysed, we tried various different lengths of the system here. We always came with the same fundamental frequency, which was based around the length of the system from here, the choke valve, to where it joins into the manifold. Okay? And the question is, you see here we're talking about closed and open. Okay, let me show you what we're talking about closed. So this is if we're talking about a dead end on one end, and we have here an open connection. So say this is a dead end branch and this was closed, fully closed, we have a closed open system. Okay? And then you see for the fundamental, we've got a quarter of the wavelength. Where wavelength drops like so, back down. Okay? An open would mean that you've got a fully open connection on this end. Okay? So for example, it's connected to a reservoir, and you've got a fully open where it's connected to the manifold. Okay? Given that the choke valve is going to be largely closed, because we're generating a very large pressure difference, then really we consider this to be closed open system. Okay? The choke valve is largely closed. Okay, to achieve a pressure drop of 100 bar. Okay? Now, as it starts to open, then it will move more towards an open system. Okay, so what we then did is applied at the frequencies associated with an open closed system. Okay? We applied the unbalanced forces to the piping system. Okay? So we applied the unbalanced force as 2% the valve pressure drop times the area. Just for simplicity, I've just shown one, but we applied that for all the straight sections of pipe, and also made some compensation for very short sections. Okay? And what I show on the right is the frequency response based on the second mode. So if we go back, second mode being these mode shapes. Okay? Showing, and what we're saying, part 1, which is this section here, the inlet. Part 2, this long section to about here. Part 3, this section. Okay? And what you see is some excitation of the mode here, around 20 odd hertz, but generally the amplitude is very low. Okay? Maximum stress is less than 1 megapascal. Okay? What's also important here to note is we've actually done a frequency tolerance. we've not just said the frequency, the second harmonic is 20 hertz. We've actually added a tolerance to account for the fact that there's some uncertainties in the flow conditions and also some uncertainties in the model that we've built. So typically, here we've got a 10% tolerance, and that's 10% tolerance on, we've analysed both the open, closed, and open, open, and then a 10% tolerance on both. Okay. Okay, so we've looked at the flow-induced turbulence and the acoustically induced fatigue downstream of the choke valve. Now we're going to look at how we analyse vortex shedding, okay, the flow-induced vibration. Okay, so we said already it's going to occur from the dead leg branches. Okay, now in this system we have the short dead leg branches here, short dead leg branches just here, and also the longer branch further down the header. So look at both of these. Okay, when do we get vortex shedding? Okay, now this graph is taken from the method presented by Rogers in a paper from 1992. Okay, and I'll explain this more in the next couple of slides, but I'll just show you. You will get vortex shedding if there's an overlap between the vortex shedding modes, which is shown as the gap between the blue lines, the red lines, and the yellow lines. So this is 1 mode, 2 mode, 3 mode. Okay, and this is the velocity and the head of velocity. Okay, on the vertical axis, these are the natural frequencies of the dead end branch. Okay, and if you have an overlap between the two, then you can have vortex shedding. Okay, so how is the horizontal axis? How are the shedding modes actually calculated? Okay, so it's how we've got this blue line. How is that actually calculated? Okay, based on experimental data, this formula was produced. Okay, and this is the radius of the opening, so the dead end branch, the diameter ratio between the branch and the header, the Mach number of the flow in the header, and the Reynolds number, and then a tolerance that was added to it, which is why it explains why you get two lines. One is the plus tolerance, and one is the negative tolerance. Okay. Now, this is a constant, Struart number. Now, Struart number is a non-dimensional frequency, much like Reynolds number is a non-dimensional velocity. Okay. And you can turn the Struart number into a frequency using the flow velocity and the diameter of the header. Okay? And what we see here, as you increase the header velocity here, then the frequency will also increase. Okay? Which gives us the reason why there's increasing amplitude with header velocity. Okay? And what we'll see is there's different relationships for the first harmonic shown in blue, the second harmonic in red, and the third harmonic in yellow. Okay? Okay, now we're going to look at the vertical. How do we calculate the acoustic modes for the dead leg branches? And here, if you remember, we talked about on the earlier slide open and closed systems. So what is the frequency of an open closed system? What is the natural frequency? And here, say this is the side branch, and this is the open closed. This is your first harmonic. Okay, this corresponds to the purple line here. And then if we go to the second mode, where we've got 3/4 of a wavelength, then we'll move up to the green line here. And as with the vortex shedding modes, there's a tolerance on this calculation. Okay? So here you see you've got overlap, and this is where we could have vortex shedding downstream. Okay, what I'm going to show here is just looking at the two types we have. We have the short branches with the double block and bleed valves, and we have the longer branch. Okay, and we see the short branch, the natural frequency of the branches is very high, looking at 300 Hertz, based on the very short length of these branches and the small dome. Okay. Whereas if we look at the long branch, we see that the natural frequency is much lower. Okay. And now we see there is an overlap between the second and the third modes. Okay. So we can say, first of all, the short branches, there's going to be no vortex shedding, no problem. For the longer branches, there is a possibility there's vortex shedding. The question is, What sort of analysis? Can we do a more detailed analysis? Check if it's going to be a problem for fatigue. Okay. Well, first of all, if we want to do a stress calculation, we need a pressure associated with the vortex shedding that we can actually put into our stress calculation. Okay. So what is shown in the method is how to calculate the normalized amplitude for a given frequency. Okay. And the normalized amplitude for a given mode. Okay. So this is the calculation for the first mode. If we go to second and third mode, then there'll be a reduction. Okay. And this normalized amplitude can then be converted. Sorry, it should be pointed to there. Converted to an actual amplitude A. So it's A bar converted to an actual amplitude A. Okay, using the dynamic pressure of the system. Okay. And what we end up with, based on the header Reynolds number, this is for a given, this is for our system, we just shown. We have the header Reynolds number, and you see that the amplitude of the vortex shedding increases with the Reynolds number. Okay? And for this was a typical Reynolds number for a gas system of around, it's a logarithmic scale, so around 3 million. Okay? And what we see is we can expect a frequency of around 10 kilopascal. Okay? Now you're going to ask why is there a step at this point? This is because over a Reynolds number of 16 times 10 to the 6, the method from Rogers just proposed a standard straightforward limit of 10 for this value, and is not dependent on any of these parameters. Okay? But most typical systems will be below the 16 times 10 to the 6. Okay. Okay, so we've calculated a pressure, so let's say for our system here, around 10 kilopascals. So now, as we've done for the other unbalanced forces, we'll simply times that pressure by the cross-sectional area and put that into the piping model downstream of the intersection leading to vortex shedding. Okay? Okay. So that's case. We looked at one case. Okay? The next question is, which one we're going to look at is a thermal transient assessment of a nozzle intersection. Okay, just give you an example of the problem we've dealt with. What you've got here is on the left-hand side you have a vessel. Okay, so it's got 3 meters diameter, and we've got a nozzle diameter of 12 inch. Okay, and we've got, this is our temperature profile coming in there. So it starts around 30 degrees, rises up with time, and reaches around 250 degrees. Then, for one reason or another, we've got a sudden change in the process temperature, and it decreases in a matter of minutes down to 50 degrees. Then a little bit further decrease, then the cycle begins again. The question is, what impact, how do we account for that in our calculation? Okay, well first of all, why do we need to account for it? So what we've shown here is the water temperature in the vessel shortly after this decrease. So I've gone here from 250 down to 50 odd degrees. And we're showing here the water temperature. Okay? And you see that the nozzle is cooled very quickly to 50 degrees. Okay? What we see then, the vessel itself has remained at around 200 degrees. Okay? Now, why might that be? Well, inside the nozzle, you've got a very fast moving flow. You've got the same volume, same mass flow rate, has to go through a small cross-section area. So then we end up with, say, a heat transfer coefficient of around 2,000 watts per square metre per Kelvin. Whilst in the vessel, we're looking at only around 300 watts per square metre per Kelvin. Okay? And what you'll see that the nozzle is trying to contract inwards. You see here that it's not exactly straight. Okay? The nozzle is trying to contract inwards, but it's restrained by the stiffer vessel, which is remaining at 200 degrees. Okay? And this is leading to a large stress intensity at the intersection between the vessel and the nozzle. Okay, just to explain the transient phenomenon, what we've plotted here is the temperature and the stress at a number of points. So we've got point A, B, and C. And what you see is number A is point A. The red line is point A. And you see here the temperature drops almost instantaneously, whereas the green line and the blue line, which are B and C, decreases more gradually. Okay? If we then plot the stress line, stress intensity, what you'll see, you see that the stress, point B, increases drastically, then decreases again as the temperature of the vessel increases, well, temperature of the vessel decreases, see the blue line, to become the same as that of the nozzle. Okay? And then you've got no temperature difference between the nozzle and the vessel. Okay? So, what I plotted here just is the steady state. So if we were to analyse this just with the steady state analysis, you would miss this large stress that's occurring due to the change in the process temperature. Okay, so how would we've got stress, so what we then did to analyse this is we analysed it in conformance with the European norm 13445. Okay, and what we did here is we selected what is the critical region. I don't know if you're familiar with the code, but the code will show a number of different scenarios. For example, is it the toe of a weld? What sort of weld connection is it? And is it set on nozzle or is it set through nozzle? For this section, which shows this crotch corner. So it's a forged component, but you see there's a crack propagating from the radius, from the outer radius. Okay? And what it will say, depending on the testing group, so this is testing class 1 or 2, or testing group 3, which curve you should use, which design curve for your fatigue analysis. And what we've done is we've taken the stress across and moved, and that gives us the number of cycles. Okay? What's important to note here is this is based on range, the stress range. So I'm saying we've made the assumption here that this, during the sharp decrease, well, not assumption, we checked it, the sharp decrease leads to large temperature gradients within the material. This more gradual increase led to much smaller changes in difference in stress between the two regions, and therefore did not lead to thermal stresses during the heat up. You see this is based on, this is over 30 minutes, it's based over best part of an hour. Okay. Okay, so for the last case I want to address, we're going to look at vibrations in a process line. Okay, we show first of all the system, and then we did an analysis based on using vibration measurements according to the VDI, and then because that showed that action was required, we then did a more detailed fatigue assessment. Okay, so this is the system. We've got a reboiler. You've then got a header coming out around 20 degrees and 20 inches diameter and 350 degrees Celsius. This then feeds 3 heat exchangers. What we're seeing in the field is you're seeing that there was a swinging motion of this header around the vertical axis. Okay? Due to the flow within it, it seems to be a constant swinging motion of the header. Okay? Now, measurements were taken. Okay? So we placed a sensor on the head at various points, measurements were taken. Okay? So the velocity profile formed a peak, and this was then compared with the limits from the VDI. Okay? A number of points were chosen, compared, and it was seen that they all lay, some in danger, some in correction, and it was determined that it did not conform with the VDI guidelines. Okay? So the question was, what more detailed analysis could be done? Okay? Well, the decision was taken to do a stress analysis. Okay? Using a pipette, using Caesar and the dynamic module. Okay? Well, first of all, we need a boundary condition. We've only got velocity measurements, but how do we tailor our Caesar model to be able to do that? Well, the first step is we need to convert our velocity to displacement, which we could do in such a manner. And here, omega is the angular frequency. So it's in radians per second in Pascal instead of hertz. Okay? Now what's interesting to note here is the relationship between displacement, velocity, and acceleration. Okay? So what we're showing here, this graphic is taken from the Energy Institute guidelines. You see you've got, for a constant velocity, at frequency, keep the velocity. As the frequency increases, then the acceleration will increase, whilst the maximum amplitude will decrease. Okay? So what this is saying, if we measure a velocity, we'll get a different value depending on what the frequency of our measured value was. Okay? Then what we need to do is convert the RMS value, the root mean squared, to a maximum amplitude. Okay? And we've converted that using the RMS value divided by 1 over the square root 2. Okay, so what we've done, similar to what we've shown before, we'll add unbalanced forces to all the header sections. Okay? Now, these unbalanced forces were calculated based on some knowledge of the flow occurring within the pipeline, within the header. Okay? And it's also iteratively changed. Okay? We knew from the measurements, we knew we had a displacement of around 1 millimeter. Okay? And what we wanted to do is say, okay, we put on at the beginning 50 newtons, and we saw that we only ended up with a displacement that was roughly the half of what we actually got from the measurements. So then we increased, obviously it scaled linearly, so then we increased it to 100 to get very close to the observed measurements. Okay? And we applied these forces as harmonic forces through a whole frequency spectrum from 0 Hz through to 10 Hz. Okay? Determine which was what frequency was most affected by the unbalanced force. Okay? Okay, now just to show you which resonance modes we saw being excited by the unbalanced forces. Okay? So here in mode 1, see here you've got a vibration in the X direction. Okay? Whilst here, so you've got a vibration in the Z direction. Okay? And what's important to note is what the effect of friction in your system is on the vibration modes. Okay? You have the option to vary the dynamic friction factor. Okay? And what I want to just show you here is what the difference is between having no friction on your system. So for example, if you've got a very large abrupt force, say times a startup or a Waterhammer, or with a startup with a steam hammer, then we thought it was more typical to have no friction, okay? Because of a very small contact area and a very large force, okay? But in this case, given the measurements we'd actually seen, and we knew it was being excited by a relatively small force, 10 newtons is not a lot, 100 newtons is not a huge amount, we did not see any movement of this header, because friction was enough to overcome, the dynamic force was not enough to overcome the friction, okay? And then, so adding friction onto these supports, we saw that we ended up with mode shapes which more like what we saw in reality. Whereas here what you're seeing is very much a movement of the header in the X direction, which was not observed from the measurements. Just to give you an example of, you have the measurements, but also it's important to have a look at what modes are actually being excited if it's experiment in the field. Okay. So, what we then did is we said we've tailored our unbalanced force to give the same displacements as we'll see in the measurements. Okay? And what we saw, and I said earlier, based on the flow conditions, we actually suspected it was a relatively broadband force that was varying between a number of different frequencies across the frequency range. Okay? And therefore we calculated the displacement to solve at the peak a number of different resonance modes. So the two modes I showed, you saw that you had a frequency of, maximum amplitude of 1/4 of a millimetre, and here you have maximum amplitude 3/4 of a millimetre. Summing those together, slightly conservatively, gives us a maximum amplitude of 1 millimetre. Okay. And this is very close to what we actually saw in the measurements taken from the field. Okay, so we've shown this a number of times, we've calculated stresses. How do we actually analyse them? Okay, well, for example, we take a curve from a pressure vessel design code. Okay, this is permissible using 31.3. Okay, and what's typically used is what's called there's no endurance limit officially given in the boiling pressure vessel code, whereas in the AN 13445 there is endurance limit given. But the limit for 10 to the power 11 cycles is equivalent to 100 Hz for 20 years. So for most practical purposes can be considered to be an endurance limit. Okay? And if we plot our calculated stress, we saw a stress level here of around 10 megapascal. That is lower the endurance limit. So although we failed the VDI limit, by guidance from VDI, we can still say it's not a problem from a fatigue perspective. Okay. Now what's important to note is we've used a design curve from another code. So I've calculated my stresses and piping analysis, but I'm using a design curve from a pressure vessel design curve. My fatigue curve is from a pressure vessel design. And what's important to note is what is the basis of your stress intensification factor. Okay? So most high stresses occur at locations with stress intensification factor, for example with T. Okay? And the T curve in section 8, division 2, is based on smooth bar. Okay? SIF perfect specimen. Okay? Whereas if you go to B31 codes, then SIFs are based on a butt weld. Okay? And the butt weld have a SIF of around 2 compared to smooth bar. Okay? And therefore, if you want to use such a fatigue curve with B31.3 results, then B31.3 stress levels should be multiplied by 2 to use this design curve. So the calculated value, say, is 20, you divide by 2, and that is your equivalent value for use in the design curve from section 8. Okay? Okay. So I've shown you there a range of different examples and how to analyse different dynamic phenomena. And as I say, I've shown a wide range of examples and how you can include them in your calculation. Now it's not possible to cover every single different dynamic phenomenon, but I hope we've given you here a range of different options that are available to you. And like I say, the big point to get is there's different methods that you can use to analyse. And that ranges through from a geometry or process-based limit, which is simple, especially helpful for the screening stage, to identify where you need more detailed analysis. You've also got vibration limits, which are certainly useful for analysing measurements, vibrations in the field. And then you've also got stress-based limits. These are much more time-intensive to calculate, but will also give you the most accurate results to determine whether something is a fatigue problem. Okay, that is presentation.
All right.
Okay.
All right. Thank you, Richard, for this nice presentation.